So if I set the Earth moving in that direction, we've got a force at right angles. Hopefully what you see from that is that the force and the velocity are at right angles to each other, which is exactly what you have for circular motion, where this force provides a centripetal force. So the whole idea is that that is the reason why the Earth orbits around the sun. Okay, it orbits around the sun because its speed is just about correct, and the force is always at right angles to its velocity. Notice how the velocity doesn't increase because it doesn't actually do any work, so there's no energy transferred, but what you get is you get this circular motion. Now, one of the things about orbital motion, we're going to come back to that later on. One of the things I need to do really is to show you some of the formulae to do with orbital motion. So I'm going to stop my share for a brief moment, and I'm going to just change my camera to this weird one that I've got hanging around my neck because it actually points at my desk here. So what I'm going to do is I'm just going to show you the basic physics, the basic formulae involved here. So if you've got something moving in a circle due to gravitational forces, then the gravitational force is equal to the centripetal force. Okay, now if the two are equal, what you end up with is an equation. The force of gravity, I'm going to ignore any signs, any positives or negatives here. If you've got the Earth, you've got the gravitational constant, mass of the Earth, the mass of the sun, can be any way around you like. Let's say that's the mass of the Earth because it's a small m, over r squared. That gives you the gravitational force. You've seen that before. And then you've also got centripetal force. The centripetal force is m. Now, you could use a couple of different formulae. I'm going to use omega squared r. Remember that omega is the angular velocity. And if omega is the angular velocity, we know that that is the same thing as 2 pi over the time period, because if you think about it, the time period is the time taken to go around one circle. The angle subtended by going around in one circle is 2 pi. Okay, so what we can do is we can then include that into the formula. So we've got m, and now I've got 2 pi there. 2 squared is 4, pi squared is, well, pi squared, r is r, and it's over t, so it's t squared because omega is squared in there. And we end up with some interesting formulae that we can actually use. You can see straight away, for example, that in here the mass of the Earth, the mass of the thing going around in orbit, is not affected. So we end up with that gm, well, we can start to sort of rearrange it and make a bit more sense here, can't we? We can put t squared on this side by multiplying both sides by t squared. We can put r on this side by multiplying both sides by r squared. So you end up with 4 pi squared over r cubed. And you end up with a formula that gives you the time taken for a planet or a moon or a satellite to complete one orbit. That's going to be t squared equals 4 pi squared over big G, big M, r cubed. And in fact, the time period squared is proportional to the radius of the distance between the center of mass of the two objects cubed is actually one of Kepler's laws. Kepler was somebody who did a lot of astronomical observation. So when it comes to using these formulae, what you actually do is basically this, but a variation on a theme. So the best way really to get you to learn to do it, to get you to learn how to use it, is to give you some examples. So on my attachment, I've got some past exam questions, which I think are quite useful ones. I've picked some relatively straightforward questions. Before I do, I just want to show you a few things. just want to show you a few things. First of all, there's the formula sheet. In the front of an exam, you always get a formula sheet. So what are we really looking for here? Well, the bits we're looking for are the gravitational constant, that's big G that big G value, which is 6.67 times 10 to the minus 11. Notice the units, newtons, meters squared per kilogram squared. And if we look on the formulae, there isn't really much that's very, very useful. We haven't done gravitational potential yet, but that is one particular formula that you might come across a little bit later, but we'll cross that bridge when we come to it, as so to speak. So I want to talk you through how to answer those questions. You have to excuse me, I'm going to work from notes here a little bit. What I'm going to do is I'm going to start the answers to each question, and then your task is going to be really to review the video and complete it, okay, and complete the questions. And what I'd like you to do, you can either produce your answer on lined paper, or you can word process a document and attach it. I don't mind, but I'm going to ask for that handed in next week. So we start off with a typical question. So we start off with a question that says that the orbit of the Earth is, you've got mass of the Earth there. We say it's assumed to be a circle with a radius, so we're given the radius of that circle with the sun at the center, as illustrated in figure 1.1. Okay, it then also gives you the time period, so that's pretty simple. So as per exam technique, what we do is we highlight, we underline, or otherwise make obvious the things that are important. We got the mass of the Earth, we've got the radius of the orbit in meters, and we've got the time period in seconds. So we don't have to convert any units. The second question will require you to convert those units. Now, if we go through some of this, we've got we're going to calculate first of all the magnitude of the angular velocity. So this is using what you know about circular motion. So the magnitude of the angular velocity, well, that's going to be, the angular velocity is going to be the angle subtended, which is one circle divided by the time taken to go around in one circle. So it's 2 pi over t. So it's literally 2 pi over our value for the time taken for one complete orbit. Okay. Now, the next thing we do is calculate the magnitude of the centripetal force acting on the Earth. Now, is a clue here. It says centripetal force. You could try and calculate the gravitational force, but you don't know the mass of the sun, so you can't do that. So we're going to use the centripetal force is m omega squared r. Now, you know m, that's the mass of the planet. You've just worked out omega squared on the last question, and then you multiply it by the radius, which remember is this value just here, okay? It does help sometimes if you actually put some symbols next to the key values so that you can see what they are. Okay, that's the first one, first part. Then the next part of the question is going to ask you to state the origin of the centripetal force. Well, the clue is here is the fact that the origin of that centripetal force is going to be the gravitational pull of attraction between the Earth and the sun. And then you have to determine the mass of the sun. How do we go about doing that? Well, we know the centripetal force. And we know that the force is big G, the gravitational constant, which is on a formula sheet, times the mass of the sun, times the mass of the Earth, over r squared. So that one, the force, was calculated in A part 2, okay? We know the mass of the Earth, we're given it. We know G, it's on the formula sheet, that's on the worksheet I've given you. And we know r squared, that's in the question. You can work out the mass, you can therefore work out the mass of the sun, because the mass of the sun is simply going to be the force of gravity times r squared over mass of the Earth times big G. Simple as that. So that's the first question. The second question is very similar. It says state Newton's law of gravitation. Now, when you're stating Newton's law of gravitation, I'm going to give this to you because when it says state the law of gravitation, a lot of people will just write F equals big G, big M, little m over r squared, which is essentially correct, but it's not really what it wants. It wants a statement. So it's the idea that the force of attraction is proportional to, well, first of all, that's a constant, isn't it? So the things that can change are the mass of the two objects. So it's the product of the mass of the two objects. So it's proportional to the product of the mass of the two objects and it's inversely proportional to the square of, well, you should say the distance between their centers of mass, but I think in this question, it's sufficient to say the distances apart, okay? So that then gives you your answer to part two, to part A. Then you got part two. Now, part B, sorry. Part B says the Earth and the Moon may be considered to be an isolated in space, so you can ignore the gravitational pull of anything else, where the mass is concentrated at their centers. The orbit of the Moon around the equator is given by that. So it's the Moon around the Earth. There's your R value. The period of the orbit is 23.7 days. So you've got to work out a time period. So it's 27.3 days. Well, we know that there's 24 hours in a day and 3,600 seconds in an hour. So we end up with, if we multiply the number of days by the number of hours in a day by the number of seconds in an hour, we get the orbital period in seconds. That's before you've even started. It then says, show that the angular speed of the Moon as in its orbit around the Earth is about 2.66 times 10 to the minus 6 radians per second. So what we're basically doing is we're using that formula that we looked at before. So, okay, the angular speed is the angle divided by the time taken. So we know the angle is 2 pi, because that's 2 pi radians, divided by time period t, which we worked out up here. So it says show. So in other words, what they're looking for is substitution into that formula. The next part is the mass of the Earth. So we're given the mass of the Earth this time, but we've got to try and work it out, and we should get something similar. Well, what we're doing is we're looking at the idea that the mass of the Earth, if we try and work it out, well, that's going to be, can we work it out this way? Mass of the Earth, mass of the Moon, divided by r squared. Are we given the mass of the Moon? Let's have a look. Are we given the mass of the Moon? If the Moon will be considered, we're given the distance, we're given the angular speed, and are we given the mass of the Moon? No, we're not. So what have we got to do instead? Well, what we've got to do is try and work out where it's, you have to excuse me, you have to try and work out another way maybe, or have I missed something? Let's have another look. Well, what we've got to do is use the idea. So I'm just trying to find my notes. Yeah, so we've got to use the idea that it's also equal to the centripetal force, which is m omega squared r. So now the mass of the Moon cancels. We know omega squared, we know the radius, we know g because it's on the formula sheet, so we can work out the mass of the Earth. Okay, so that's how we do that one. And then you've got the mass of the Moon. So you're told the mass of the Moon now. It says, using the data from part B, determine the gravitational force between the Earth and the Moon. So we're literally just using F equals big G, mass of the Earth, times the mass of the Moon, divided by r squared. And then we're just substituting in values. So we want to work out the gravitational force. Well, we know the mass of the Earth because we're given that from from B part 3. We know the mass of the moon because we've given it there. We know R because we're given R earlier on in the question, so we can work out the force, okay? And that should bring you to the end of that particular exercise. So I'd like you to have a go at doing that. Notice how I've not given you any answers. I've just shown you how to do it. I want you to go through and have a go at answering those questions. Okay? Do you have any questions? Romania?
Yeah, no, I don't have any.
Okay. Do you think you can go through that? So it's downloadable from Show My Homework. So you go on the Show
Okay.
My Homework task, and all you need to do is download the worksheet. If you can either print out the worksheet and then scan in your answers, or you can produce your answers on a Word document, or you can write them down on a notepad and take a photo and upload the photo to Show My Homework. Is that okay?
Okay.
Okay. Well, thank you very much for watching. I did say it'd be quite short. Have a go at doing that. And if you hand that back in, I can mark it and I'll check that we've understood that bit before we start moving on to potential and energy. Okay.
Okay.
Have a nice weekend.
You too. Thank you.